All right, section 9-3 is on rapid repeated integration by parts. And the objective of this section is to use a pattern to quickly integrate by parts. In the last section, if you recall, we learned this integration by parts technique and how we can use it to evaluate an integral of a product of two functions. And in some of those problems, you saw that you had to use that technique a couple of times. You went through once and found how to rewrite that problem in terms of a new integral, but that still wasn't simplified enough for you to find the integral, so you had to use integration by parts a second time or a third time. So that's the idea of repeated integration by parts. You've already seen that. But it turns out in that process, you're actually writing some things down more than once. In fact, you're writing some stuff down that you really don't need to write down. And so we can speed up that process a little bit by eliminating some of those things. And so that's the rapid part of this, the rapid repeated integration by parts. So let's take a look at an example here first, and we'll quickly go through this using the technique you learned in the last section and find what the integral of this is, and then we'll see what we can actually eliminate from this process and see what happens. So let's pick u. U will be equal to x squared, and dv is going to be equal to the e to the x dx. All right, so then we find that du is equal to 2x times dx. The derivative of x squared is 2x times the differential. And we integrate the dv to find v is equal to e to the x. And we've already talked about how we can eliminate the plus c there, so I'm not going to worry about writing that down. So we have the integral of x squared e to the x dx. We're writing down the original integral, and you're going to want to write that down every time. That's equal to, it's u times v, so it's x squared times e to the x. In other words, notice here we're taking the product of these two guys right here, kind of that diagonal right there that we're multiplying. U times the v. And then it's minus the integral of v times du. So that's the e to the x times 2x dx. Notice that we're integrating this bottom row right here. So we're multiplying those two together, the v times the du. Now if you look at what you have here, you've simplified it because you went from a quadratic function times the exponential function that you're integrating to over on the right side, now it's a linear function times that exponential function. Let me just rewrite this slightly. So it's x squared times e to the x minus, I'll put the 2x out front, times e to the x dx. But I still can't integrate what I have there, so now I have to look at how to integrate that part of it. And so we use integration by parts again. So we make this time u equal to the 2x, and we're going to make dv equal to the e to the x dx. And so you end up with du is equal to 2 times dx. And when we integrate the dv, we end up with v is equal to e to the x. All right, and so now when we write this down, again, I'll write down the original problem here again. So we have the integral of x squared e to the x dx, and that's equal to, again, the first part of this stays the same. We didn't mess at all with the x squared e to the x. But now it's that integral of 2x e to the x that we're changing. I'm going to put this in parentheses so we don't lose this minus sign that's out front. So it's u times v, our 2x times the e to the x. Again, you're multiplying those, again, that diagonal that we're multiplying right there. And then it's minus the integral of v times du. It's that bottom row again, e to the x times 2 dx. That is, you're integrating this bottom row right here. All right. So let's see what we end up with here now. We have x squared e to the x. Let's go ahead and distribute that minus sign through there. So you have a minus 2x e to the x. And then you got a plus when you distribute that minus sign through, minus that negative there. So it's plus the integral of 2 e to the x. That's just going to be 2 e to the x. And then a plus c at the end. All right, so that's the process that we are going through. Let's take a look at what we've written down and what we can kind of gain from looking at this example. First of all, you'll notice that this original problem here, when I picked u and found out what du was equal to, I got 2x. And down here, the next choice that I made for u was the exact same thing. That happens many times when you're repeating this integration by parts, that whatever you ended up with for du becomes your new choice for u. We're writing it down twice, though. That's kind of a waste of space there, writing that down twice. We're going to eliminate writing it down twice. Not only that, but you'll notice that what we ended up with for v here, in the first iteration of this, became our new choice for dv the next time. So again, you're writing that information down twice. And the other thing that you'll notice here is that we're actually writing down the differential that we come up with when we are finding du. And we're also starting out with that over here when we write down what dv is equal to. Well, we know the differential automatically is going to go in this problem, so there's no reason to write that down. And we can do the same thing down here. There's no reason to write the differential down as I take the derivative. There's no reason to write it down when I start with dv. Just simply write down what the integrand is. Don't worry about the differential. And so now you can see how we're going to simplify this problem quite a bit. Not only that, but notice the signs that you end up with here at the end. The first term here doesn't have a plus out front. I'll just add one in there, but there's a positive x squared. Then it's negative, and then it's positive. So you'll notice the sign alternates. Okay? And each time here that we are doing this, if you look at the blue arrow there, we were multiplying that diagonal, and then we are integrating the bottom row there each time. Okay? So those little things there that we saw from this problem can kind of help us come up with some techniques we can use to simplify this problem. Let's go through those. Here's the rapid repeated integration by parts technique. The first thing that we're going to do is make a column for both u and dv. So we're not going to write down u equals each time. We'll just make a heading at the top, u, and make a column for u's, and then dv and make the column for all of our dv's that will go there. And then as we do this, we take the derivative or differentiate the u column. That's what we're doing every time to find du. We take the derivative. And we integrate the dv column. That's how you found v. You integrated dv to do that. And then we're going to multiply down each diagonal. We saw that. That was that blue arrow we had a second ago. We're going to multiply down each diagonal. And we got to integrate that last row each time. So whatever the bottom row is, we got to integrate it. And then finally, alternate signs. We saw that in that example there that it changed sign from positive to negative back to positive. All right. So let's go back and try this example again, but let's try it with the rapid repeated technique. This is going to be a much faster way to come up with a solution. Now we've already done this once, so we know what the answer is supposed to be, so we can check our answer there, of course. Let's see what we end up with. First of all, my choice for u is going to be x squared to start off with, and my choice for dv is going to be e to the x. Notice I'm not writing down the dx there. Again, that's kind of extra information I don't need to write down. I know what goes there. Take the derivative of the u column, so I get 2x. Take the antiderivative of the dv column. I get e to the x. Do it again. Derivative of 2x is 2. Antiderivative of e to the x is e to the x. And in fact, it turns out if I can get 0 in that u column, it turns out to be pretty nice. So I'm going to take one more derivative. We'll get a 0. And take the antiderivative of e to the x again as just e to the x. We'll talk about what the techniques are that we know when to stop this process, but getting a 0 here in the u column is one stopping condition. Now, we said that we multiply this diagonal, and then we integrate the bottom row. And the other thing that we said in our technique was we got to alternate signs. You start out with positive every single time. It's always positive for the first diagonal, then it's negative, then positive, then negative, and it keeps alternating. Right there is our answer. We just got to write it down. So we have, let's rewrite the original problem again. We have the integral of x squared e to the x dx. That's what we started with. And now just follow your arrows here. You've got x squared times e to the x squared e to the x. And then it's minus the 2x e to the x. And then it's plus the 2 times e to the x. And then it's minus the integral. Remember, you got to integrate that bottom row. That's why I draw that in a different color there to help it remind us of that. The integral of 0 times e to the x. And I know there's no dx that we were writing down, but I know a dx goes in this problem. We've been leaving that out so I didn't have to keep writing it down every time. I just got to remember to put it into the problem there. at the end. Now to write our final answer here, we have x squared e to the x minus 2x e to the x plus 2 e to the x, and we're actually integrating 0. If you think about that, you've taken the derivative of something and got 0. The only way you get 0 is if you took the derivative of a constant. So the antiderivative of 0, this is why getting a 0 there is really nice. The antiderivative of 0 is just your plus c. There's our answer. Okay? Definitely a much faster technique than what we saw the first time we tried this problem. All right, let's talk about the stopping condition. When do I know to stop this process of integration by rapid repeated integration by parts? So the rules to stop the rapid repeated technique. All right, the first thing is if the last row, if the product of the last row is 0, you're done. Because if you keep taking derivatives there of that 0, obviously you're going to keep getting 0. So that's not going to do anything for you. So if you get to a 0, that's actually really nice. We saw that it turns out the integration is already done then for you, because it just turns out the integration of 0 is plus c. All right, if the last row can be integrated, so if you look at that last row and you go, oh, I know how to integrate that, then that's another stopping condition. Again, sometimes that happens, like the last problem that we just did, but by going one step further, you might get that 0. And I would definitely recommend you go to that next step if you can. But if you can integrate the last row, stop. The third one is if the last row is a multiple of the original, the very first row. And we'll see that happen here. Sometimes you start out with, a product of two functions, and then you end up at the bottom row 1/2 of that product, or 1/3 of that product, or whatever it might be. If it's a multiple, it doesn't have to be a half or a third. It could be 5 times that or whatever. Then that's a stopping condition. If you have a multiple of the original. And then finally, if the last row is a trig identity of the original. So sometimes these problems, especially if it involves a trig function, you got to watch out for some trig identities to show up. And for the most part, it's the Pythagorean properties is what we're going to look for. And we'll look at an example that has that here in just a bit. All right, so that's our stopping condition. That tells us when to stop this process. Let's look at another example here on page 439. The integral of e to the 6x cosine of 4x dx. Now again, you're going to pick a u and a dv, but we're just going to make a u and a dv column, remember? We're going to go through this rapid repeated technique. And I got to pick something for dv every time that I can integrate. I can integrate an exponential function and I can integrate a cosine function. So I'm set with either one. Doesn't matter which one you pick. However, I'm going to pick e to the 6x as being the dv, and I'm going to pick the cosine of 4x as being the u. And the reason for that is because sometimes that when I take the derivative of sine and cosine, I'm okay with the plus or minus that shows up in that process. But that antiderivative of sine and cosine, sometimes that's a little bit tricky. Wait, is this one the positive or the negative one? Versus e to the 6x, it doesn't matter whether you take the derivative or the antiderivative, it's basically the same. So let's set it up this way. So if I take the derivative of cosine, the derivative of cosine is a negative sine of 4x times the derivative of 4x, which is 4. I'm going to go ahead and put that minus 4 actually out front. So we have a minus 4 times the sine of 4x. And for the antiderivative of e to the 6x, it's just going to be e to the 6x times the reciprocal of the derivative of 6x. Derivative of 6x is 6, so those are 1/6 out front. All right, let's do that again. Take the derivative of sine of 4x, that's going to be cosine of 4x. But I got to multiply by the derivative of 4x, which is 4, times the negative 4 I already have out front, which gives me a negative 16 cosine of 4x. And do the same thing over here for the antiderivative of 1/6 e to the 6x. You're going to get e to the 6x, but then I have to multiply by another 1/6. So you have 1/6 times 1/6, that's 1/36 e to the 6x. And actually, this is one of our stopping points. If you look at the very first row, which is cosine times e, and look at the very last row, you've got some constants there times cosine times e. So you have a multiple of the original integral. So this is a stopping point for us. So here's the first diagonal, here's the second diagonal, and we're going to integrate this last row. As far as the signs are concerned, plus, minus, and plus. There we go. Our answer's sitting right there. We just got to write it down. Actually, you're going to see there's a little bit more to this one. Let's write down our original integral. It was the integral of e to the 6x cosine of 4x dx. And that's equal to, so we have, I'm going to put the 1/6 out front here, I guess. So I'll have 1/6 e to the 6x cosine of 4x. And then it's minus, but there's a negative there. It's a negative 4x. So it's going to turn out to be plus here. And then it's 4 over 36. I'll go ahead and write it that way. We'll simplify that here in just a second, but we'll write it out that way first. 4 over 36 times e to the 6x times the sine of 4x. And then finally we have plus, but it's got a negative 16 there, so it's going to actually be minus the integral of. You've got 16 over 36. I'll write it that way to start out with at least. And then e to the 6x times the cosine of 4x dx. All right, so let's rewrite this here just a little bit. So we've got the integral of e to the 6x cosine of 4x dx on the left side there. That's our original integral. 1/6 e to the 6x cosine of 4x. And then 4 over 36, let me just rewrite that as 1 over 9 e to the 6x sine of 4x. And that constant, let me pull that constant out front, but let me simplify it also. You got 16 over 36, so those both have a factor of 4. So you ended up with 4 over 9 times the integral of e to the 6x times the cosine of 4x dx. Now, if you look at what you ended up with here, this is why this is one of our stopping points, is because on the left side I have the integral of e to the 6x cosine of 4x dx. I have that same integral over on the right-hand side, the integral of e to the 6x cosine of 4x dx. And just like you learned way back in algebra when you were first solving problems, when you had two quantities, they're both x's or both a's or whatever variable you're working with, and they were on opposite sides of the equation, you just simply moved one of those quantities to the other side to combine them all together. That's all we're going to do here. I've got one of them on the left side, and I've got a minus 4/9 of that integral on the right side. So if I take the one that I have on the left side and add the 4/9, 1 plus 4/9 will actually give you 13/9. So we have 13/9 times the integral of e to the 6x cosine of 4x dx. Again, what we've done is I've taken the one that I have right here on the left side. In fact, let me go ahead and put a 1 out in front, or on the left side. And then I've got the 4/9 over on the right side that I was subtracting. I add those together. And now on the right side, I have the 1/6 e to the 6x cosine of 4x plus a 1/9 e to the 6x, oops, e to the 6x, times the sine of, oops, that looks like I've left off an x up there. It should be a sine of 4x. And of course, the integral that was at the end, I've moved already over to the left side. And now, to solve for my integral, again, I'm looking for what this integral right here is equal to. All I got to do is get rid of the constant, that coefficient out front. So multiply through by 9/13. So you have the integral of e to the 6x cosine of 4x dx is equal to, it's going to be 9 over 13 times the 1/6 e to the 6x cosine of 4x plus 9 over 13 times 1/9 e to the 6x sine of 4x. And usually we wait till this point to put our plus c in there. Technically, it should show up in the previous step there just because of the fact that that's where you got rid of the integral. We usually wait till this step just simply so that we can don't have to worry about that constant getting multiplied through there. And let's just simplify our constant here now. When you have 9/13 times the 1/6, they've got a factor of 3 there that you can cancel out. So you end up with 3 over 26 times e to the 6x cosine of 4x plus the 9s will cancel out in the next one, so you have 1/13 e to the 6x sine of 4x plus c. There is our antiderivative of that function. All right, let's try one more of these. And if you look at example 2, they have the integral of sine squared of x dx. Now, when you look at that initially, you might say, well, that doesn't look like a product. All the other ones we've been working with, they looked like a product when we started out with. But of course, squaring something is the same as multiplying it by itself. So if you want to, you could think of this as the integral of sine of x times sine of x, because literally that's how we're going to split this one up. So it turns out that even if you have powers of functions, that you can think of those as products as well and use this integration by parts technique. So let's try that out. We'll pick u and dv. I'm going to pick part of this, the sine of x for u, and the other part, sine of x for dv. Again, that first row that you write down, that product there has to be the original problem. Sine times sine gives me sine squared. That's what I start out with. Take the derivative of sine. Derivative of sine is cosine, and the antiderivative over here of sine is a negative cosine. Okay? Now, we didn't get our 0, and we're not going to get a 0 out of this thing. The last row doesn't look like a multiple of the first row, but remember, another one of our stopping techniques was if there's a trig identity you could use to get the first row, then stop. And the first row is sine squared. The second row here now is cosine squared. I know there's a trig identity that relates those two, so that's a stopping point for me. So we only had to do this once. Oops, let me do that in red is what I've been using. So we multiply the diagonal, integrate the last row, alternate signs, and so we end up with the integral of sine squared of x dx. Again, always write that down. You saw that in the last example, why we do that. And now it's sine times a negative cosine, so it's a negative sine of x, cosine of x. And then it's going to be minus a negative, so it's actually going to be plus the integral of cosine squared of x dx. All right, and now that cosine squared that we have over there, there's a Pythagorean property that I know that relates sine squared and cosine squared. So we have a negative sine of x, cosine of x, that stays the same. But I'm going to replace cosine squared here. I know that sine squared plus cosine squared is equal to 1. So that means that cosine squared is equal to 1 minus sine squared of x. All right, basically if you know your 3 Pythagorean properties for your trig identities, that's the 3 that you need to know. All right, now let's rewrite this over here on the right-hand side. You've got a negative sine of x, cosine of x. And then I'm going to break this integral up here as the integral of 1 times dx, or just dx, and then minus the integral of sine squared of x dx. And you can see now, I should have been writing this down on the left side here. Let me go back and do that again. You can see what I have now is I've got the same integral on both sides, similar to what we had in the last problem. I've got the integral of sine squared on the left, and I've got minus the integral of sine squared on the right. So I'm going to combine those two. Add the sine squared that I have over on the right side there to the left, so I end up with the integral of, oops, I should have 2 of them. And 1 on the left, and I'm adding the 1 on the right, so it's 2 integral of sine squared of x dx. And that's equal to negative sine of x, cosine of x. The integral of 1 dx, I can integrate that. That's just simply x. Again, technically at this point, the plus c should show up there. We usually wait till the next step so I don't have to worry about this constant that I'm about to get rid of on the left side. So divide through by the 2. So you end up with a negative 1/2 sine of x, cosine of x, plus 1/2 x, and then put your plus c there at the end. There's our antiderivative of this function. And again, you can see the technique at the end looks similar to the previous example because of the fact that you ended up with the integral on this, the same function on both sides there. All right, that's as far as we're going for this part of this section.